Okay, so let's start with the solution of the quiz. Now the area vector will be in the z direction. A is equal to, let's say, pi r squared in the z direction. This is the area vector. The magnetic field is uniform, so the magnetic flux is nothing but A dot B. And if you just multiply them, only the z component contributes. So you have minus 2 Tesla times pi, which is approximately, let's say, 3, times r squared is 5 times 10 to the power minus 2 meters squared. So this will be, let's say, minus 125 10 to the power minus 4 Tesla meter squared, or minus 1.25 times 10 to the power minus 2 Weber. So this is the flux, yes?
Will it be the right thing? Because I calculated the theta, cosine theta, with these two vectors, and I got the same answer as correct.
I mean, whichever, if you could calculate the angle between the area vector and the magnetic field vector, that's fine. $1.5, right? Okay, now let's go back. We have this inductor. So, do you agree that an inductor put in a circuit will resist any change in the current? And could you follow the reason? Yes or no? No? Any questions on that? Why does it resist? Some reaction? Well, Lenz's law, you can say. Well, basically, the Lenz's law arises because the changing current will create a changing magnetic field, which will create an induced electric field, and this induced electric field will try to prevent the change in the current. So, for example, if you change the resistance to try to change the current running through your system, or you change the EMF of your battery, the inductance will also resist it. So the change in the current will only happen slowly. It will not happen instantaneously. It will just happen slowly. Now let's look at the circuits. We can imagine putting a circuit in our system, putting this inductor in a circuit. This is probably the simplest circuit that you can think of that contains an inductor. And let's also add a switch. Let's say the switch is closed at t equal to 0. What is the current as a function of time? How does the current change as a function of time? And this battery has an EMF epsilon. Now again, we can just use the Kirchhoff's rules. I mean, they will still be valid. The only addition to the Kirchhoff's rules will be this one. The EMF induced by an inductor is just the inductance times the time derivative of the current running through it. So let's start from, let's give some names, A, B, C, D, E. And we have a single loop. What is the potential drop as you go from A to B? Well, let's start from C to D. When you close the circuit, from C to D, what is the potential drop? 0. From D to E, minus epsilon from E to A. Let's say this is the positive direction of the current. So there is a potential drop, and that potential drop is I times R. Do you agree that it should be plus? Now the tricky part will, okay, from A to B, 0. Now the tricky part is kind of from B to C. Let's say it will be L di by dt. Is it positive or negative? Why? Anybody else? Okay. Okay, first of all, the inductor does not oppose the current. The inductor opposes changes in the current. So you have to consider the changes in the current. So let's just consider as an example, suppose the current is, at a given time, the current is increasing. We don't know, but let's just assume at a given time the current is increasing. So in that case, you are right, it will try to oppose the current, the change in the current. So it should be, since the current is increasing, it should create an EMF in the opposite direction. So that is why it has, if the I by dt is positive, then this creates tries to run the current in the opposite direction. So that is, it is just as if we put such a battery over there. So the potential drop from B to C will be positive. Could you follow it? What we are trying to do is just consider the case when di over dt is positive. The current is increasing. The current is increasing in this direction. If di by dt is positive, the inductor will try to prevent it. That is, it will try to run a current in the opposite direction to reduce this increase. But if it is trying to run a current in this direction, it just mainly means that this is at a larger potential than this one. So there is a potential drop as you go from B to C. Now let's do the other case. If di by dt is less than 0, the current is dropping. Then the inductor will try to push the current in the positive direction. Well, that means this point will be this will be higher potential, this will be lower potential. Just if you just consider a battery, this will be similar to the positive terminal of the battery, this will be similar to the negative terminal of the battery. But that means the potential drop should be negative as you go from B to C. But that also means L di by dt is already negative because di by dt is negative. So there is a plus sign. Whether di by dt is increasing or decreasing, the sign over here is plus. So L, the current, basically satisfies this equation, di by dt, L plus I times R, this is equal to epsilon. Now, how do we solve this equation? I will just write the answer. The answer to this equation is I of t is equal to epsilon over R. This is eventually what it will become. Plus h power minus T over TL over R, no, TR over L, times some number. We don't know that number yet. So if you just take this expression, put it over there, let's do it. di by dt. This is equal to, this is just a constant, so a times minus r over L times e to the power minus tr over L. This is di by dt. So if you just put this in L di by dt plus I times r, this is minus ar e to the power minus t r over L plus epsilon over r plus a times e to the power minus t r over L times r. So this term, no, not that term. This term will cancel this one. This one will cancel this one. This is equal to epsilon. So it's actually a solution, whatever the value of a is. So this is the solution for this equation. Now, how do we determine a? We know the initial condition. At t equal to 0, that is when we close the circuit, the current running in our circuit is 0. The current didn't build up yet. This is equal to 0. But at the same time, this is epsilon over r plus a. So this should be 0. So it basically tells me that a should be equal to minus epsilon over r, or I as a function of time is epsilon over r times 1 minus e to the power minus t over tau. Tau is L over r. So this is how the current changes as a function of time. Now if you would plot it as a function of time, at t equal to 0, it is 0. The exponent e to the power 0 is 1, 1 minus 1 is 0. As time goes on, this number gets smaller and smaller. So this whole parenthesis approaches 1. And so if this is epsilon over r, so it approaches that value. So this is how the current changes in our system. It doesn't increase very fast. It just increases slowly. And the time it takes for it to take a significant value depends on what this tau is, the time constant. Tau is called the time constant of this circuit. Now, as we said before, what this inductor is basically is just a wire. It doesn't have any resistance. Its resistance is 0. But its inductance is non-zero. Now, before considering the effects of the magnetic fields, we had said that the current just increases instantly to its final value. But we see that any inductor in the circuit will just cause it to increase gradually to its final value. This is one thing you can always keep in mind. In physics, there is almost never any jumps. Nothing jumps from one value to another value. Everything changes continuously. And this inductance is basically what causes it to change continuously rather than having a jump. Now, what happens if you open the circuit, by the way? Will it go to 0 straight away? But you see, I have, let's just imagine these are my conductors. They are carrying the current. My switch is closed. Then I open the switch. So if you are saying that it is decreasing slowly, then after I open it, it should be flowing for some time. So how does it flow? Heat? Well, the current cannot be transferred into heat. The energy in the current can be transferred into heat. But remember, current is nothing but the flow of electrons. If there is a current, there should be a flow of electrons. You cannot transfer it to something else. Electrons cannot change into something else. They stay as electrons. Okay. Okay, they will heat, they will lose energy. They are constantly losing energy as they are crossing the resistor. But the question is not about their energy, the question is about the current. So when I open the switch, how does the current behave? You said that the current doesn't go to zero because there is an inductor which will try to keep the current at its value. But that means the current should be flowing through the circuit for some time. It might be a very small amount of time, but for some time the current should be flowing. But the switch is open, so how does it flow? Okay, so how does the current, where does it flow? There is an open circuit. I open the switch.
Elektrik field'ın ışığı yaptığını söylemiştiniz. Onu kaldırdığınız elektrik akışı durduktan sonra bir süre elektrik field orada işini devam mı ettiriyor?
Now I'm talking about the current here. The current should be flowing because of the inductor. How does it flow? Through the air. Correct? Haven't you seen any sparks when you turn off a switch? No? Come on, tonight, go home, close all the lights, close the curtains, and turn off the lights. And you will see a spark, a very slight one, if it is not well isolated.
Why should we see the spark? Why should we see the spark?
Why does the spark come into the game? Well, what? Where? At home? On the switch. I mean, you cannot just break the circuit instantaneously. It takes some time. Well, if you try to break it instantaneously, what happens is this di by dt term. You are causing this to be infinite. But if you are causing this to be infinite, you are creating an infinitely large potential across the switch. But that is already large enough to cause an electric breakdown of the air. So there's a slight spark. Yeah, over there also. Which is not a nice sight. Okay, by the way, I forgot to show you this one. Any questions on this one, by the way, up to this point? Here I have a circuit with no battery. I have a solenoid over here and a lamp. So since there's no battery, the lamp doesn't light up. Now we put it in a region where we will be creating a magnetic field. Well, it should go through, but it doesn't for some reason. Well, nothing happens. Let's increase the magnetic field. So basically here what I have is, well, there is one circuit over here which contains this solenoid. There is another circuit over here which contains a second solenoid. And when I run some current, well, the current running through the system is changing in time constantly. So So when I run a current through one of them, it creates a current on the other one. On this one, there's no battery, there's no switches. Now, if this would have went a bit more down, what you would have seen is that even without this rod, there you would see a slight faint light. With this one, it gets brighter. Now, okay. So let's imagine this one. We have one solenoid. We connect it to a battery and a switch, etc. Then we put another solenoid around it. And we connect this to a different circuit with the light bulb. Let's say at a given time, the current running through this one is I1, and the current running through the other one, let's say I2. Now, what is the magnetic field created by this current I1? Which is, no, the magnetic field. V1 is just mu 0 I1 times N1. Well, this creates a flux in the second solenoid. This is the flux created by V1 in the second solenoid. Let's also show it by Phys110. What is Phys110? You see, if you imagine, this is our second solenoid. This is our first solenoid. I1 creates a current, a magnetic field in this one. This is our B1, in that region only. Well, that creates a flux in the second one. Which is nothing but pi R1 squared. It is R1 squared because the magnetic field is non-zero only inside the first solenoid. Times B1 is mu 0, I1, N1. This is equal to times N2. N2 is the number of turns. So pi R1 squared mu 0 N1 N2 times I1. Now this is Phys110 is the flux created in the second solenoid due to the current in the first solenoid. And this Phys110 is just some number, L. Now let's call it M. I1. M is what's called the mutual inductance. It is the inductance of one circuit on the other one. It's a measure of how two different circuits influence each other through their magnetic field. And of course, then we can talk about the induced EMF in the second one, which will be due to the current in the first one. It is just M times di1 by dt. This is basically why we have light here in the circuit. There's no electric field, there's no battery connected to this circuit, but when I put it over here, this solenoid over here creates a changing magnetic field, and hence it creates a changing magnetic flux in the solenoid of my circuit. And that changing magnetic flux in my circuit over here creates an EMF, which runs a current, which drives a current in my other circuit, and that current is what causes us to have light.
Is it possible to the same equal EMP first solenoid and second solenoid?
Equally?
Is it possible to equal the magnitude of EMP?
E and B. Well, what are their units?
I mean, is it possible to the magnitude of same magnitude?
Well, what are their units? If you want to have two things have equal magnitudes, they should have the same units. Do they have the same units? Yes, let's see. Force is equal to Q times E plus V cross B. So the unit of E is equal to unit of V times unit of B. They don't have the same units. You cannot compare their magnitudes. Okay, any questions? Now, before you ask a question, let me ask a question. I mean, we will not proceed with this circuit. But you see, let's suppose we have a time-dependent current running through the first circuit. Let's just assume that this battery has a time-dependent EMF. So if this has a time-dependent EMF, the current will be changing in time, but this solenoid will have what we call the inductance or self-inductance, which will resist the changes over here. But anyway, the current will be changing. So as this one is changing, it creates a changing current in the second solenoid. But the changes in the current running in the second solenoid will create a magnetic field, an additional magnetic field, which will create an EMF in the first solenoid, which will also change I1. So the rate of change of I1 will depend on the self-inductance of this one. It will also depend on the rate of change of the second current. Okay, this is just to keep in mind. I mean, things are getting complicated, so that's why we will not proceed along these lines, but the basic idea is that the current running in this I1 also depends on how much current has been created in I2. So you cannot just solve this circuit ignoring I2 for the I1. But still, just to keep in mind, there is this concept of mutual inductance. It will be important in our future discussions, but for the time being, I will just leave it here. Yes. Huh?
I just want to review the equations I just
Okay. Other questions? Are you following what we have been discussing in the last couple of days?
But it comes that in breaking air.
In?
Breaking air. A large amount of voltage is required.
In breaking?
I mean, in breakdown, the breakdown voltage of air.
Yeah, true.
It's very high. So, in the previous example, you said that we will see sparks.
True.
And if the breakdown, I mean, if the voltage across due to the inductance of the inductor is not up to the breakdown voltage of air, why will we see sparks?
Well, you see, the EMF across the resistor, across the inductor, is L times di by dt. If you don't see sparks, that means I, from a given value, it goes to 0 instantaneously. But that means di by dt is infinite, which cannot be, which is larger than the breakdown voltage of air.
Okay, what of if at the point where I, that is at a particular point in time, current flowing through that will be 0?
Now, I can be 0.
When it is connected, when the battery is connected, it will that is.
Now, if I is 0 at a given instant, you can open the circuit, no problem.
If you open the circuit,
Nothing will happen, sure. But if you start from at a time, let's say in this circuit, this is constant. So when you close the switch, the current will start building up, so it will never be 0 again. So it will never be 0. If you open the switch, you are just trying to drop it instantly to 0, but that means the EMF created by this inductor will be huge. That will be enough to create this spark.
Not through the air, but we try to do switch, open the switch in another material or something that has a breakdown voltage more than in order to.
Well, you see, whatever the material is, you put your switch in different kinds of materials, assuming the current goes from some finite value to 0 value instantaneously, means this di by dt is infinite. So L times di by dt, which is the EMF created by this inductor, will be infinite, which is larger than the breakdown voltage of any material.
So what I was going to say was still about the breakdown things. When we open the switch, what happens is that there are charges accumulating on one end. So that's why we see spark. Because one of the charges moves to the other side. But if we consider that the EMF created EMF that still exists after when we open the switch is not strong enough, we won't see a spark because the potential difference won't be high enough.
Well, it depends on the capacitor is a metal, right? So as you said, charges will accumulate, which means there will be a potential difference building up. How much charge you can accumulate without creating a huge potential drop will depend on the capacitance of the switch itself. It's not a capacitor, but at the end of the day, it's just two conductors separated by a gap, which is a capacitor. If the capacitance of the switch is high enough, you can actually prevent a spark. Basically, what will happen is the current, even after you open it up, the current will keep running, and there will be a charge accumulated in the capacitance of the switch. and eventually the current might just drop to zero
Or
without creating a spark.
the capacitance might be low, and the stored charge might be low as well. It's also.
Okay, now, are you following what we have been discussing in the last couple of weeks, the changing magnetic fields? Well, of course. I mean, if it was of course, I mean, if I weren't seeing so many sleeping eyes, I would have said, of course. No, let's just review what we are actually doing. I mean, just an overview, not a detailed one. So what we have been discussing up to last week, we were always in statics. We were dealing with cases which didn't change in time. The only exception was when we had the capacitor in a circuit. That was a system that was changing in time, but we ignored any possible modifications to our equations. We assumed that statics, the equations we have for electrostatics, is valid also if it is changing in time. Now, what we have been doing is that we are looking at time-dependent systems, where we started with this discussion of a rigid rod moving in a magnetic field. Then we had some inconsistencies in our expressions, inconsistencies in the sense that what should happen seems to change as we change our reference frames, which shouldn't happen. Well, the only way that we could avoid it was to claim, that was our hypothesis, to claim that a changing magnetic field should create an electric field. That is the only way we could avoid it. So that led us to the Ampere's law, no, the Faraday's law. And then we have been basically studying what is this electric field, how do we create it, what will be the influences of this electric field created. Now, of course, we started with the EMF, but EMF basically is created by an electric field. So if there's an EMF, there should be a created electric field. And then we said that, at least just to visualize what is going on, if you have moving magnetic field lines, now why should the magnetic field lines move? Well, if you are changing the magnitude of the magnetic field, that means you are changing the intensity of the magnetic field lines. So if magnetic field is changing, then the intensity of the magnetic field lines should be changing. But in order to change the intensity, the magnetic field lines should be moving. And if the intensity is getting larger, there are more magnetic field lines approaching a given region. If the intensity is getting smaller, there will be additional magnetic field lines approaching that region, but in the opposite direction. So they will just cancel the existing magnetic fields, lower the number of magnetic field lines. And well, that is basically all we have been discussing in the last couple of weeks. Now, then we had this new device called the inductor. So basically now, if you just imagine the circuit elements, we have a battery as a circuit element, we have a resistor as a circuit element, and now we have an inductor as our circuit element. And the resistor, it just resists the flow of the charges, well, from the name also. So given an EMF, given a potential difference across a resistor, so there should be a given current running through the resistor. The capacitor was acting somewhat differently. If we just connect the capacitor to a circuit initially with zero charge, it just acts as if it is not there. But if the current runs long enough that the capacitor will be fully charged, after that it just acts as if it's an open circuit. It doesn't allow the current to flow after some time. So that is the two extremes of a capacitor. Initially, without any charge, it just acts like a short circuit. With fully charged, it acts like an open circuit. Now, the inductor, on the other hand, it just resists any change in the current. So if you just try to start the current from zero, it acts like an open circuit. In a sense, opposite to what the capacitor does. Remember, if you just connect the capacitor to a circuit and close the switch, initially it just acts like a short circuit. But the inductor, as we had seen in this example, the inductor, if you connect it to a circuit and close the switch, it just acts as if it has an infinite resistance at t equal to 0, so that there is no current running through it at t equal to 0. Of course, eventually the current builds up. If you wait long enough, the capacitor just acts as if it is an open circuit. It doesn't allow any current to pass through. Whereas in the case of an inductor, if you wait long enough, it just acts as if it doesn't exist. It's a short circuit. So that is basically the main differences between capacitors and inductors. In a sense, they just behave in an opposite manner in a given circuit with time. Any questions? Well, the inductor, this is the shape of this is how we show it in the circuit, but the shape is not really that important. An inductor is anything that has this property. Anything that has this property is what we call an inductor. Anything that resists any change in the circuit, in the current running through it. That is what we call an inductor. And as I said, even if you don't put an additional inductor in your circuit itself, if it has a finite area, itself has a finite inductance. Because it will be creating, if you run a current through your circuit, it will be creating a magnetic field, and if the current is changing, the magnetic field will be changing. That will create a changing magnetic flux, and it will create a EMF that will oppose the change, even if you don't put an additional circuit element. That kind of makes it difficult to construct circuits that have whose currents should be changing fast. For example, in your CPUs, they have their clock. What that basically means is that the current should be changing its direction at whatever the clock speed is.
Can you review the torque of a square loop? Can you review the torque of a square loop?
The square loop. Where is the square loop? The torque.
Yeah.
Okay, so let's go for a break now. In the last hour, I will start with reviewing the torque.